All right, and so let me begin by connecting my phone so you can kind of see my work here. And while the phone is connecting, let me read the question here. All right, actually, I'll write it down on my paper here. Let's see. Nice. Okay, so chapter 32, number 44. All right. And actually, I printed this one, the second page, because I kind of messed up here. And this is the one that didn't copy, but it looks like you got the second page, and I sent a reminder of that. But it says in the active circuit 3215, and you know what? I better look that up, but I think that's an LCR circuit, if I'm not mistaken. Number chapter 32. What one did they say? Figure 15. Oh, okay. That's not, I'm glad I looked it up. That's not what I was thinking here. But let me keep the book here handy and read this. So an active picture, R is, actually, let me go ahead and copy it onto the screen here. But 15 looks like this. It's got a power supply that has an EMF of script E. Looks like it has a single pole double throw switch. And they got the switch in A, and with the potential of moving over to B. B then has the inductor and the resistor in it. The other branch has the capacitor in it. Okay, and so there's our active circuits. Okay, so back to the question. In active circuit, active figure 3215. Let R be 7.6 ohms. Let L be 2.2 millihenry. And let the capacitor be 1.8 microfarads. A, calculate the frequency of the damped oscillation in the circuit. All right, now, if you set up the equation and solve it, it's actually a second order differential equation. So the book said that perhaps you more want to just prove that this is the equation, not so much that this is how you solve it. And so this is one of those problems where it's kind of a step above the math you have, but not too much. Like if you didn't have the resistor in there, or you can see it in this equation, R equals to 0, it's actually pretty easy to solve this one. It's not too much out of the realm of your mathematics. This one with the resistor is a second order differential equation. It's not too bad. It's one of the easier second order differential equations, but it's still second order differential equations. And so without going through the proof, although if you want me to, I will, but I like the way your author said. Your author just says, why don't we just accept this as the possible answer and see what it should be equal to. In fact, maybe I'll just write it out. He says, Q then would look like this. It would be some starting value, some maximum value, and the capacitor would do two things, essentially. It would decay and it would oscillate. And in the decay, He says if you go through, you will find, let's see, must be a 2L down there. Yeah, 2L. This is the decay due to the resistance as it oscillates back and forth. And then there would be some oscillation that would go on. And then this omega sub D, this dampening, is what he said would work out if you put that equation. So again, I think the best way to do this problem is to begin by saying, this is the solution of what would happen when you have a capacitor and an inductor and a resistor in series. And the best thing to do is to take, you know, this equation and put it into this Kirchhoff's loop, and you'll see that it works out if omega D is equal to that. So sure enough, it does work. And so that's where I'm going to begin the problem anyways. I'm going to begin with just saying, this is what the author gave us. And then it really just becomes a plug and chug. So it does require you to kind of recognize that what's going to happen when you move this switch from A to B is you are going to get a charged capacitor because it was sitting in A for a while. And by moving it from A to B, as you're moving it, the capacitor remains charged. And then you put it here, you have some maximum charge on it. And it's going to then oscillate. And each time it oscillates, it loses a little energy. So the amplitude's going to decay. So this thing in front of the cosine function is its amplitude. And it's going to go with this frequency. And without any resistance, it's just the famous square root of 1 over LC. That's the easier one to solve. So this one just says calculate the frequency. So, all right, I will go. And he's not real clear whether he means frequency or angular frequency, what we call linear frequency. I think he wants linear frequency, but let's see what the answers tell us. But I'm going to go then and do this calculation. So this is 1 over, so the L is 2.2 times 10 to the minus 3. That's the millihenries. And the capacitance is 1.8 times 10 to the minus 6. That's the microfarads. The resistance is the 7.6, so quite a bit of resistance. So this is going to have probably a significant effect. Kind of curious to what it is. And then 2 times the inductance, which we said is 2.2 times 10 to the minus 3, and then we will square that. So just out of my own curiosity, without any resistance, if this was kind of what we might call an ideal perfect circuit, I would have this 2.2 times 10 to the negative 3 times 1.8 times 10 to the minus 6. And taking the reciprocal of that would be 2.53 times 10 to the, 1, 2, 3, 4, 5, 6, 7, 8. And just out of curiosity, if that's all there was, all right, so this would oscillate at about 16 kilohertz. But we're going to subtract off, and so this is going to lower the frequency because of the resistance a little bit. 7.6 divided by 2 divided by 2.2 times 10 to the negative 3. Square that. And we're looking at 2.98 times 10 to the 1, 2, 3, 4, 5, 6. So not too much. This is 100 times smaller than that. So it's about a 1% effect. So this thing would oscillate pretty much at the same rate as if there was a little resistance, or really the resistance isn't big enough to really even show. And I was just curious about that because that's kind of very common for circuits that even though they have resistance in them, ignoring them sometimes, which isn't completely true, gives you about the same frequency. So, all right, but if I do this right, then let me come back to the 2.53 times 10 to the 8 and subtract off the 2.98 times 10 to the 6th. And now let me do the square root of that answer. And we are looking at about 15,812 hertz for the frequency of this thing. So that,
Dr. Young.
Yeah.
So I've seen, so there's another equation that's like F equals 1 over 2 pi root LC.
F equals, little f probably. F equals?
Yeah, 1 over
1 over
2 pi, and then root LC.
Oh, okay.
What is that?
Oh, okay, good. Great question. Let me give myself another page here. So when you talk about frequencies, it can be a little misleading. This omega is actually what we would call the angular frequency. When somebody says frequency, they usually are talking about linear frequency, F. Maybe you remember this back in Physics 121, where the angular speed is 2 pi f. So f is what we often call the normal frequency. How many times does the wheel go around? Let's say the wheel goes around 2 times in a second. We would say the frequency is 2. When you multiply it by 2 pi representing how many radians would go on in one circle, this then becomes how many radians would rotate, or how much the wheel would rotate in radians. So this technically is the frequency, this technically is the angular frequency. So you might argue that what I did was not complete, because what I've just done is the angular frequency. So I really need to take my omega and divide it by 2 pi. So I need to take my 15,812 hertz and divide it by 2 pi. And I know I haven't quite gotten to your question yet, but I think, let me do this first and it'll hopefully fall into place. So this is a frequency of 2,516 hertz. So if the author is asking for, when they say frequency, the angular frequency, I would stop there, but I suspect that they're not, but I don't really know, because it's hard to tell, because when people talk about frequency, sometimes they'll carelessly mean angular frequency. But if I read his words more exactly, what I just solved for is the angular frequency. This is what I would put into an equation if I said cosine omega t, because omega is 2 pi f. And so when you're doing a mathematical calculation, you want in radians, you don't want how many times does it go up and down or oscillate, you want how many radians does it do. So when it comes to mathematics, we often are more interested in the angular frequency. When it comes to trying to understand the physics, we're often more interested in what we just call the linear frequency. That is just how many times does it oscillate. All right, so finally I can get to your question, because your question, if you look at this equation that you said F equals 1 over 2 pi LC, I'm going to write it like this, 2 pi, and then 1 over the square root of LC. That right there, this 1 over the square root of 2 LC is the angular frequency that you would get if you ignored any resistance. So if this was a circuit that didn't have a resistor in it, then the equation you read to me would be the appropriate combination of two steps. Number one, getting the angular frequency, and then number two, dividing it by 2 pi to get the linear frequency. So this is a great equation, but it's a combination of two equations that if you're not careful, you may not notice that this 1 over the square root of LC is actually the simple case of an LCR circuit without any resistance. So it would not be appropriate for this question. This question clearly has a resistance. So, this is only good if R equals 0. Now, that being said, I did point out, as I was doing this calculation, that for a lot of our circuits, this number is so big that unless you have a lot of resistance, you can pretty much ignore that. And so if you use this equation, I bet you would get something very, very close to this 2,516. In fact, I'm going to give it a try. If I go 2 times pi times the square root of L, which is 2.2 times 10 to the negative 3, and then the C, which is 1.8 times 10 to the negative 6. And now I take the reciprocal of all of that. Yeah, really close. 2,500, and I get 29 instead of 16. So I would say that this is off a little bit because it didn't include the resistance. But a lot of times, we're only interested in 2 or 3 significant figures anyways. So this equation wouldn't be what we might call very reasonable. Completely right, no, but very reasonable. So now you got.
So if I had taken, on some of the previous questions, if I had just taken what I calculated using the equation they have in the book, which is square root of 1 over LC,
Yeah.
and I just divided it by 2 pi, I would have had the right answer.
Yeah.
Oh, okay. I didn't see that. I thought I was using the wrong equation the whole time, but.
Yeah, no. And so I'm kind of curious now that, I'm going to scroll through the answer here. Yeah, so they did what I did, and they included the resistance, and they got 2,500, and they rounded it to 2 significant figures. Well, they go 10, so I would have rounded it up, but anyways, other than a little bit of rounding, and then in your case, if you just did this one, you would have ignored the resistance. But I think this one, the intent in 44 is to try to point out, don't ignore the resistance. The one before that, 41, doesn't have any resistance.
Yeah, that's just exactly the equation that we just talked about, the 1 over 2 pi.
Right. So the equation we just talked about, this one here, is the one that would be exactly right with no resistance. And like I said, in the practical world or the implied world of engineering, sometimes we are. I know I've done this many times. You just say, oh yeah, there's resistance, but it's small, ignore it, and it's an easy calculation. And other than the last significant figure, you're pretty accurate and accurate enough to go on. In fact, I'm kind of curious then what the second part of this is, because maybe that's what they're trying to do, is to see how it compares to something without any resistance. Oh, they don't. They go on to say, what is the critical resistance? Now, that's a fancy word that you may not have caught, because if you want to know my thinking on this, I want you to be able to really understand LC circuits really well. To go all the way to the LCR circuits, I think we're kind of bordering on the next level, either the next level in physics or the next level in your circuits class. And I think you are in circuits, so you're probably doing a lot of this in your circuit.
Not well. I think we're supposed to be, but we're like about a couple weeks behind. Yeah.
You're behind. So okay.
Yeah.
Well,
I mean, we started inductors, but we haven't done anything with them yet.
Okay. All right. So, yeah, one thing interesting about the circuits class and this class is sometimes you see one before the other, and I suppose that makes it easier in the class you see it the second time.
Yeah.
So,
well, we did capacitors and resistors out of order, and we did resistors first in the circuits class.
Yeah, and that's pretty typical of a circuits class. The physics follows more natural with capacitors, then resistors, and then inductors. But a circuits class, the kind of resistors are kind of more natural first because you just want to deal with current and flow, and the capacitors are a little more complicated, I guess. Anyways, I guess I was trying to say maybe that will encourage you to say, okay, it's a little complicated now, but it'll pay off next week or the week after when you start doing this in your circuits class. Yeah. But let me mention this critical damping. I'll put this equation again. The angular frequency for damping is 1 over LC without any resistance. Then if you have some resistance, that resistance reduces the frequency by either a little or a lot, depending on how big the resistance is. And what's called critical would be something, maybe a picture would help. Back here with the charge on the capacitor, if I would make a plot of this, I see there's a cosine function. And in front of the cosine function, which we often call the amplitude, is a decaying exponential. So this might look like this. Here is a cosine function where its amplitude decays away. So this mathematics here would be represented with a plot. So here's maybe charge on the capacitor and time. And so it oscillates, but with each oscillation, the amount of charge, that is the amplitude, goes down and down with this decaying exponential effect, which has to do with the resistance. Now, what's really interesting is right here, this frequency can go down and down and down and eventually become 0. And if it became 0, you wouldn't even get an oscillation. You would just get this kind of because cosine of 0 is just 1. And so as long as this number is not 0, as long as it's still positive, you get some oscillations. Like you might get something look like this. You might have omega kind of small, so it would go and maybe oscillate twice, and then that's the end of it. Should have done that in a different color. But if you get all the way down to where omega sub d is 0, you don't even get a single oscillation. And you would have, your physics would have said, wait, I have a capacitor and an inductor. I should get some oscillations, but you have put so much resistance in it that you've stopped it from oscillating. In fact, if I can do a mechanical comparison, the shock absorbers on your car are exactly this, that if you just took the suspension, which would be a spring, it should, make your tire oscillate. So when you hit a bump on the road, it would, bump your tire up, and then your tire would keep shaking like a spring and eventually dampen out. If you put a shock absorber in there, you could give it enough resistance so that the spring, which gives it its oscillations, and the resistance from the shock absorber give you a omega of 0, and so you don't get any oscillations, and so the tire hits the bump and then goes back, maybe one small oscillation. And so your tire just, doesn't make you and the car go like up and down for the next 30 seconds down the road. It goes and settles right back in, getting ready for the next bump. And so a mechanical engineer would study this equation in terms of a spring and the shock absorber. An electrical engineer would study this equation in terms of the current flowing in an LCR circuit. Well, I kind of tried to give some helpful application of it, but I was using all that to get to the meaning of what is this idea of being critically damped. And that is basically saying that omega D equals 0. And so if you take the square root of LC minus R over LC and you square it, well, I'll just square it to get rid of the square roots. I get 1 over LC minus R over 2L squared. Move this to the other side. And when this condition matches, when you have so much resistance that it is equal to, to the left-hand side is equal to the right-hand side. If you have that much resistance, you don't get any oscillations. And that could be a good thing. Like I said, in the case of a car tire, that is a good thing. You don't want it to oscillate. In the case of a circuit, that, depending on what you're trying to do with that circuit, that could be a good thing or a bad thing. So now I forgot the question, all this. It says, what is the critical resistance? So what resistance would do this? So if I take the square roots, I get that. If I bring the 2L to the other side, I get that. So putting in my numbers, the square root of 1 over L, go back to page 1, what was L? 2.2 times 10 to the minus 3, and C, 1.8 times 10 to the minus 6, and then multiply that by 2, and then multiply that by L, which is 2.2 times 10 to the minus 3. So if we put in this much resistance, we would have actually then get no oscillations out of this. So that's going to have to be quite a bit of resistance. So let's see what it is. I'll take the 2.2 times 10 to the negative 3, multiply by 1.8 times 10 to the minus 6. That's this number down there. Take the reciprocal and then take the square root. Okay. Oh, well, that's not a surprise. That's that number we essentially got earlier. Okay. Then multiply that by 2, and then multiply that by 2.2 times 10 to the negative 3. And it looks like about 69.9 ohms. So check the answer. Oh, good. That's the same that they got. Oh, it looks like they simplified some math. They put the L inside before they actually punched in the numbers. Okay, but anyways, we get the same number, so 69.9. So again, this circuit, if you didn't want it to oscillate, you would just move the switch, and you put this resistance at 69.9, it would just decay away instead of oscillate. And so who knows, maybe we'd have a switch here that, radio on, radio off. I don't know. But once it's off, you don't want any oscillations. With it on, you want it to be able to oscillate. Anyways, good. Hope that helped. I think I saw some other questions here in the chat. So let's get more for me. I will jump back to chapter 31. All right, Alicia. Let's go to Faraday's law. Good. And I'll say that's all you guys have been asking on 32. Good for you. I kind of expected a lot of questions from 31, given that we just really took the test last week, and then it's hard to do 31 and move on here. Oh, good. And then Hunter's got one from 31 too. So, all right. So let me put here then for 31, number 20, and I'll put the time at 3:32. And so chapter 31, number 20, page 1. And let me then go to the questions and scroll back up here to 30. Uh-oh. Am I in the right chapter? 31. Oh, number 20. Yeah, 31, number 20. Okay. And so here's another motion EMF. All right. Let me roughly review a metal rod moving in a magnetic field before I go too far with this radio antenna, because what we called a motion EMF was to say, okay, what would happen if you just had a metal rod? So here is a metal rod of length L, and it's moving with a velocity V, and it is in a magnetic field. Let me make the magnetic field maybe not only perpendicular, but kind of going into the page. I'll get out my green marker here and put X's kind of into the page and say, okay, so here is my magnetic field. And if it makes more sense, you can make a kind of a dotted line, because Faraday law involves a loop. It doesn't have to be a physical loop, it's a mathematical loop. So like a Gaussian surface and an Ampean loop, we could just make a rectangular or closed surface. But if I did Faraday's law here, I would say the EMF produced is equal to, and we have this negative, the number of turns and the change in the flux. Now, maybe to make things a little bit easier, I'll just say, let's just look at the magnitude of the EMF. So I'll drop the negative sign. I'm just going to make one mathematical loop, because there's not really a physical loop here. Some of our problems, we actually have wires in a coil, and so our mathematical loop and our physical loop are the same, and we have many of them. But that means my N is just equal to 1. So for this problem, I will just look at the change of flux that goes on into this loop. Okay, let me take the derivative. Now let me remind you of the calculation for flux. And this is going to be magnetic flux, not electrical flux. We were more introduced to electrical flux way back with Gauss's law, chapter 24. And we used an electric field. But now we're going to do a magnetic field. And I shouldn't put a little circle on there. I have a habit of doing that. But this is not a closed surface. This is just actually a flat rectangle. Let me say that the rectangle has length L, the same as the rod. And I'll just say at this moment in time, it has moved over a distance X. So when I go to take its derivative, and I do this integral B dot dA, I would put cosine of 0, because the magnetic field going into the paper and the area vector is perpendicular to the plane. So there's my dot product. I'll even go one better and point out that for a constant magnetic field, and when I say constant, let me be extra careful now that we're doing our calculus, because when I do this Faraday's law, there is an integral in space and there's a derivative in time. So it is possible that whatever you're working with is a constant in space but not time, or the other way around, a constant in time but not in space. It's also quite possible that it's a constant of both space and time. And that's what I have here in this kind of review before I actually do the problem of a motion EMF. What I'm saying is I just have a magnetic field. So not only is it constant from space, but it's a constant in time. And so I have the same field from left to right, space. I also have the same field over a period of time, 1 second, 2 seconds, 3 seconds, 4 seconds. So that's why I'm going to take the magnetic field and pull it in not only in front of the integral, but also pull it in front of the derivative. Which then just leaves me with an integral dA, which is the area. Which we could write the area as its L times its X. And so here's a good example of where I would say the area at a moment in time has a particular value, but it changes with time. And in this case, the dimension that changes with time is the X, not the L. So I can pull the L out in front. And then I have the time derivative of X. Well, that, if you just read the math, is saying here that this is how this rectangle increases its size. This is the velocity. This is how X changes with time. So this becomes BLV, although I think in class and in your book, we derived it with a lowercase l. So this was a long way of saying that this is where you start the problem. You start the problem with saying, I know that the magnitude of the EMF is the strength of the field. Careful here. It's the strength of the field that is perpendicular to the motion of the rod. I'm going to come back to that because it depends how they describe this. Okay. But it's the magnetic field times the length of the rod times the velocity of the rod. All right. So that was kind of a review. That really is not necessary to solve this problem, but I thought it was necessary to kind of help people know what I'm going to do, because now I'm going to read the problem. So I'm going to read the problem here, and it says an automobile has a vertical antenna, vertical radio antenna, that is 1.2 meters long. Okay. The automobile travels at 65 kilometers per hour on a horizontal road where the Earth's magnetic field is 50 microteslas directed towards the north and down at an angle of 65 degrees. So if this was kind of the surface of the Earth, let me give it a little curve here, then my magnetic field, so this is the Earth and this is the North Pole and this is the South Pole, and so this is up and this is into the Earth or down. My magnetic field, which has a strength of 50 micro, oops, too high, sorry. So my magnetic field, which has a strength of 50 microteslas, is actually angled, and let's see, they gave me an angle 65 degrees below the horizontal. So if I drew a horizontal line, this would be 65, or over here, 65. And so this is probably pretty close to where we are here in Santa Barbara. We have a magnetic field from the Earth of about 50 microteslas. And we also then have an angle down about 65 degrees. Okay. Now, maybe I'll change colors, because if I'm driving a car on a horizontal road, my antenna is vertical. Now, let me go back here to my derivation. My derivation, you look at the geometry laid out here, says that I get this equation, BLV, if, we got to watch the 3 dimensions, the rod, notice the rod is moving in 1 dimension, I'll call that X. It's aligned perpendicular to that motion, okay? So that's, I'll call the Y-axis. And the field that is significant and important is the field that then is perpendicular to both of them. So it's the Z direction of the field. Because as I start to do this problem, I have this antenna that then, of course, if we're on a horizontal road, we would definitely be moving, if we moved, say, to the north this way, we would be moving, of course, perpendicular to our rod. If we moved to the, and I'll go east, it's kind of hard to draw east in this picture because it would be, you know, 3-dimensional, but this would be east. And so what I'm trying to say is this antenna can be moving north, it can be moving east, it can be moving south, it can be moving west, but it's not moving up or down. So the part of the magnetic field that is up and down, the vertical part is useless here, okay? That's what this is telling me. So I'm not going to worry about the whole magnetic field. I'm only going to worry about the part that is perpendicular to, and notice this, perpendicular to the direction I'm moving and perpendicular to the antenna. So this would tell me for this to work, this antenna actually has to move either east or west. Because if you move north, you're actually then moving in the same direction as the horizontal component. And remember, we've got a 3-dimensional configuration here. So we have to have all 3 dimensions. We have to be moving perpendicular to the field. And the rod has to be perpendicular to the field and perpendicular to the direction we're moving. And that works if we are moving east or west. And we focus our attention only on the horizontal component. So the component that's in the north. Okay, so that's why I took the extra time to say, I think we better go through a review of the motion EMF. I know I did it, and I know the book did it, but like any of these tough disciplines, it doesn't make sense the first time. You gotta see it a couple of times. All right, so that's why I'm saying again here that, okay, this antenna will produce an EMF if I match those 3 conditions. And what I'm saying is those 3 conditions are matched if I have a vertical antenna that is traveling either east or west, and the only part of the field I care about would be the part that is horizontal. That's the part pointing north, not the part that's going down. So once I know all that, this is actually fairly easy. At least I'll do maybe, I think, B first. It says calculate the magnitude of the induced EMF. So let me just write down the B, the L, and the V. Okay. The B is the part I need to be careful with. I don't want to just put 500 micro Teslas because that's the full strength of the field. I'm going to say it one more time. The part that I care about is the part that is perpendicular to both the direction I move and the rod. So that's why my rod is an antenna on a car, it's up and down. And if I move east or west, then the horizontal component does match that. So to get the horizontal, I would have cosine of this 65 degrees. So the field is pointing down. It has a magnitude of, I hope I'm reading this right. The Earth's magnetic field is 50 microteslas directed towards the north and down. So it's got components. It's got a northern component and it's got a downward component. And by multiplying it by cosine of 65, I get the northern component. And I completely eliminate from my calculation the vertical component. So that's why this B probably should be written as B perpendicular to the motion. So there it is. Now the length of it was clear, 1.2 meters long. And the velocity was clear, although my units need to be worked with. So they said 65 kilometers. Let me change that to 65,000 meters. And then I'll also do 3,600 seconds in place of an hour. And I guess I should have put my units here for the meter. So I'll hold off on the number for just a second. But if you remember your units, a Tesla is, of course, there's a lot of ways of writing it, but we originally learned the units for the Tesla was the force that 1 coulomb would have when it's moving at a rate of a meter per second. So by multiplying it by a meter here, and then another meter per second, this meter per second is going to cancel off. Then uh-oh, did I mess up here? Joule per coulomb. Oh, and that, yeah, okay, and then that is a volt. Oh, okay, okay. Drawing a blank there for a moment. Okay, so that is our volt. How do we define a volt if you remember the electric field integrated with distance? So it would be the unit for the electric field, which is a Newton per coulomb times a meter. Or maybe that wasn't the definition. The definition was how much energy do you get per charge? So joule per coulomb. So Newton meter is a joule per coulomb. All right, sorry, I drew a little blank there, but the units come out right. Good, that's voltage. Now let me grab my calculator and say, all right, let's multiply this out. So this is 50 times 10 to the negative 6 times, and we were doing some radian calculations last session. So let me switch my calculator back to degrees. Okay. So cosine of 65 degrees for the trig function times 1.2 for the distance times 65,000 divided by 3,600, and we're going to get 4.59 times 10 to the minus 4 volts. So it's not a whole lot of volts in terms of you're going to drive your car and use the voltage from the antenna to run the radio or something. That's just not going to happen. But it's the physics is still there, and that's what this is after. So there is a small amount of voltage there. Now, before I check the answer, let me go back to A, because then A then specified the direction that the automobile should move so that it generates the maximum motion EMF in the antenna. Now, with the top of the antenna being positive. Now, I answered half of that by coming back here and saying, according to this, you should really be driving east or west. That's how you're going to get the most. I probably should have specified that if you were driving, say, northeast, you could have done something like this. You could have first said, to get the magnetic field that is perpendicular to your motion, you would first have done this calculation and go 50 times cosine of 65. That would have given you how much is pointing to the north. Then if you were driving at a 45-degree angle to that, you could then take this result and multiply by another cosine of 45 to figure out what it would be if you were driving northeast, because you got to figure out how much of the field is perpendicular. But my point is that you would want to make sure that you were driving then perpendicular to this field so you can get the full effect. That's how I knew the maximum would occur by going east or west. In fact, if I went straight north, none of the field would be perpendicular to me. So my EMF at most could be this, and at least could be 0. So my motion EMF would be anywhere from 0 up to 4.59 times 10 to the minus 4. So east or west is what I was thinking to give me the maximum, and I calculated that. And so I was actually kind of already thinking about A, its maximum. But now I've got the other question: is it east or is it west? And so let's come back to here. There's a couple ways we could think of it. If we come back here and do Lenz's law, with the magnetic field going in, as this moves out, there would be more and more flux going in. So a EMF would be set up that would want to generate a current to oppose that change. So with more going in, we would want our thumb coming out. So a different color, maybe I'll put, that would make this side of the metal bar positive and this negative. Now that might be kind of hard to see in my picture with a moving antenna. So I'm going to do something a little different. I'm going to go back to chapter 29 and remember my force on my charges is V cross B. So if I just say that, look, inside of this metal rod are electrons that can move, and they are moving then to the right, and my field is going in. If I do my right hand rule, I put my fingers in the direction they're moving and then close my hand down and my thumb's pointing up. So V cross B is up. So that's the direction positives would move and negatives would move down. So I'm going to do that. I'm going to say, I'm going to call up positive because V cross B is positive. And I think that's going to make it a little easier here, because if I move to the east and my field is to the north, I would go V cross B, and that would give me the up. And so that would make the positives up. So moving to the east would be what I would want. Whereas if I was moving, excuse me, to the west, I would have done this. I would have said, okay, if the the positive charges in this bar would be moving west, and then I would close towards the north. My thumb would point down. That would push positives down. So moving to the west, the bottom of the antenna would get positive, whereas moving to the east, the top of the antenna would be positive. And they wanted the top to be positive. So there's my answer. I must move to the east. So moving to the east would give me not only the maximum, but it would give me the positive upright, or the top. Now that's for a vertical antenna. I should point out that if we angled our antenna, we could take the full strength of the magnetic field, because we want to know how much is perpendicular to our antenna. So if we really wanted this, we should angle our antenna at 65 degrees to generate the most. But they make it very clear in the problem that the antenna is vertical, as many are. I know some of your more modern cars have sloped the antennas so that they give it more of an aerodynamic look, and it looks nicer on the car because it's sloped there. But this one's a vertical one. So,
Some
and then
higher-end
of course,
cars also have the antenna in the back window, like the wire for the radio antenna implemented into the back window.
Yeah, that's kind of a nice design to bury it in there, so it gives it more of an aesthetic look and fits the form. But it's never been my experience that they work as well. They don't have the pickup. They aesthetically they're nice. Functionally they suck. Oh, can I say that on the radio?
Quick question. What is this P? I missed that in the beginning. On the top of your drawing, it says like micro, and then it has a P there. I don't know what that signifies.
Right here?
Up a little bit. I don't know. Like up on the top of the triangle.
Oh,
yeah, that. Yeah.
Sorry,
Yeah, right at the top of the screen.
that says up. That's supposed to be a U.
Oh, okay. I was like, what is P? I have no idea. Okay.
Yeah, no, that's, so this was supposed to be the Earth. And so
Okay.
kind of a cross section of the Earth. Here's the North Pole, here's the South Pole, here's down towards the center of the Earth, and here's up above the Earth.
Okay. And then in their solutions, they also said, assuming that the antenna has positive charge at the top. Is that just because charge wants to move down to the ground, basically? Or
No.
Yeah.
So when the antenna moves,
because they say for maximum induced EMF with positive charge at the top of the antenna.
yeah.
But I didn't know if that was like why they were just saying, okay, positive charge is at the top of the antenna. I guess we were supposed to just assume that because the charge would go down, like charge would move, like the negative charge would go down.
Right.
But I didn't know if the direction would change if positive charge was not at the top of the antenna. But I guess, okay, so we're supposed to assume that just because charge would want to go down towards the ground.
No, I'm not going to say it that way. I would say it this way, that when you have a moving antenna, and this picture is getting kind of messy, so I'm going to go to a new picture, same picture, but just redraw it. If I have a metal rod that is moving with a velocity v, then inside of this metal rod are lots of electrons. And so if there's a magnetic field, that means we have moving electrons in a magnetic field. And this is the equation for the force on a moving charge in a magnetic field. This is, the chapter 29. So if I had a field that is going into the paper here, these electrons that are in the moving rod would have a force, and I'd go V cross B, my thumb goes up, and then times the negative charge. That means these electrons would be forced to the bottom, not because it's down, but that just because they are moving in a magnetic field. This is what we call the Lorentz force. If the rod had been moving the other direction, let's say the rod's moving this way, and I still have the field going in, I would go V cross B times a negative, and now the negatives would move to the top of the rod.
I think your video froze. Yeah.
Terrible timing. Well, is there ever a good timing for that? All right, I'll stop sharing for a second, and usually it picks up real quick here when I bring it back. Now, so I think it froze right when I was trying this to say, what if we went the other way? So then my right hand would be V cross B times the negative would flip it over, and negatives would go to the top of the antenna. So they don't go down just to go down. They go in the direction that this force, the Lorentz force, is on them because they are moving in the Earth's magnetic field. So that's why they're asking which way would you move? Because if you move to the east, the top of the antenna becomes positive. But if you move to the west, now the top of the antenna is negative. Now it'd still be the same magnitude, so B would be the same calculation. And, hang on here, looks like the sun has come around to my window and I'm starting to warm up. I got to get out of my sweatshirt here where I overheat. All right, or maybe I'm just getting excited with the problem here. I'm starting to break a sweat here, but it seems to be getting warm here in my room. Not quite enough to open a window, I don't think, so I'll leave the window closed for now. All right, so I hope I didn't take too much time going through the motion EMF, but the motion EMF is kind of the fundamental one, and that's kind of what this class is about. Try to, get that fundamental idea of why there would be an induced EMF, but the complexity of it, or maybe I should say the details of it, about how the magnetic field needs to be perpendicular to both the motion and the rod, and which way it's moving is really what this is about, because part B is just kind of a plug and chug one, but knowing, did I check my answer? I didn't check my answer, but they got the same numbers. So they got that cosine of 65. That's what I wanted to double check, because I might make sure I was interpreting their words correctly. Okay, good. Well, I'm glad that one pans out. And I think I saw another one here. So that was number, 20. Let's go to Hunter's question, which is number 27 from the same chapter. And so I'll put here chapter 31, number 27, and say, all right, let's scroll to 27. 27. Oh, good. It's on the top here. Now here it again, and this is another motion EMF. It's a little different. It's not moving in a straight line. It's rotating. It says a helicopter has a blade of length 3 meters. It extends out from the central hub, and it is rotating at 2 revolutions per second. If the vertical component of the Earth's magnetic field is 50 microteslas, what is the EMF induced between the blade tip and the hub? Now, I won't go all the way back to our derivation of our motion EMF, but I'm going to use that as a springboard to say, remember how we just derived this motion EMF? We said if you're moving with a velocity v and your rod has a length L, and you have a magnetic field that is perpendicular, and I'll just put it in, then the magnitude of the EMF is BLV. All right. Now, what makes this one a little different is we're not just moving straight, we're rotating. So let me do this. Let me call this the center hub. Let me make the blade sticking out. Let me just have it rotating at some angular speed omega. So I'm going to end up going back to physics 121 and our mechanics here. But one thing we learned from our mechanics in physics 121, I guess it would be chapter 10, is that each point out here would move with a velocity that would vary depending on how far out it went. In other words, if r is equal to 0, this part of the rod right there would barely be moving. But this part out here would be moving with what we would say is the length of the rod times the omega. And of course, halfway in between would be L over 2 times omega. So each of these little pieces would move at a different speed. So I'm going to use what we derived for things moving in a straight line and extend it for something rotating by doing this. I'm going to say, let's look at a little tiny piece. You see, a little tiny piece would be moving with some velocity. So let me call this B. And instead of calling it DL, instead of calling it L, let me call it a DL, because I just want to take a little length of it. So not the length of the whole rod, but just a little length. And then the velocity would be R omega. And what I'm saying is this would give me a little bit of voltage. It wouldn't give me the voltage for the whole blade. But what I could do is then say that the total voltage of the whole helicopter blade is what I would get when I added up the voltage from the first one, the second one, the third one, the fourth one, the fifth one, the sixth one, the seventh one, the eighth one, the ninth one. And technically, I would chop it into an infinite number of pieces. So I would do an integral. So this would be B dl r omega. And then I would say, well, what we're talking about, this dl is really a dr. See, because we're talking about how long is it in a radial direction. So my original motion EMF was derived in terms of length, so that's why I put dl. But we should probably call this for our calculation dr, because I have an r right here. And so now I can do an integral that's based upon the dr. And so I'm going to add from r equals 0 to r equal L. And the things that don't change is B, so B I can pull in front. And the one thing nice about rotational motion, when something's going in a circle, even though each piece has a different linear speed, each piece has the same angular speed. So that's the nice way of dealing with things that rotate, is you can have them with the same angular speed. So I can pull the omega in front. And that's got to be the world's easiest integral right there. You integrate r dr, and you just get r squared over 2 evaluated from 0 to L. So this would be B times omega times an L squared over 2. So you might say that I've taken the general idea of what is the EMF produced by a straight line, made it a small straight line, and then it added it up for something that was rotating. And so this is the EMF for something that is rotating. So with that in mind, I can now do this problem, and I'll start with the magnetic field. I'll say a word of caution like the last problem, but it's not really needed for this problem. In the last problem, where did I draw that thing? And all this writing on here, remember, I emphasized that the part of the magnetic field that was useful was the part that was perpendicular both to the motion and the length of the rod. So in this helicopter problem, I think they're kind of implying that the helicopter blade is rotating in a horizontal plane. So the only field we care about is the part of the magnetic field that is vertical, which is the part they gave us. So they just said that wherever this helicopter is located, the vertical component is the 50 micro Tesla. So unlike the other problem, I don't have to take a cosine or a sine of the angle. They already just gave me the components that was important. But I wanted to just pause for a moment to say that that's what I need, and I don't have to worry about any kind of angle involved for this one. So the hard part was this integral, not the component of the field. Then the omega, and to make the units work out right, they give me 2 revolutions. That means it is 2 pi radians per second. So there's the angular speed. The length of this blade is 3 meters. So I'll square that, and I think I'm just need the factor of that 2 downstairs, which would actually cancel with that one. And then, of course, we could do the same thing, remembering our units. A Tesla is a Newton per Coulomb moving at a meter per second. We then have the unit of a per second from the angular speed, and then we have a meter squared, which I'll write as 2 meters, because then there's the meter per second that would cancel there. There would be the Newton times the meter, which is a joule, and a joule per Coulomb is our definition of a volt. So yes, it is going to work out right in terms of the units. We are going to get a volt. Now I can grab my calculator here and put in those numbers. And so 50 micro times, and I canceled the 2, so I'll just go pi. And I'll just square the 3 in my head. So there's a 9, and I've taken care of everything else. And so this would be a 0.0014 volts. Which, by the way, doesn't sound like a lot. And I was commenting about the antenna, but I should pause here, because with a helicopter's blade, this can get substantial, that small sparks come off, usually not much voltage, and they're pretty dim. You can't see with your own eyes, but at night, military operations, this is a problem, because they put on that night vision and the sparks come flying off, and it gets amplified, and you can see this really, really well. And so I bet if you just YouTubed well, probably just helicopter and sparks and night vision, you would see it. But the mask on the old sailing ships, this same thing would happen late at night. The sparks would come off as they're sailing along in the Earth's magnetic field. What did the old time sailors call it? Colonial days, when they would sail from England. St. Elmo's fire. So this is St. Elmo's fire. So if you have an extra moment this weekend, Google St. Elmo's fire, or St. Elmo's spark. No, I think it's St. Elmo's fire. So the sailors didn't understand it, but they sure knew it existed. And so it'd be dark out at sea and sailing along at night, and these sparks of light would come off the top of the mast. Anyways, That, I think, is the answer to 27 without all the question. Maybe I'll check the results here. They got 2.83. Oh, wait. How come I got half that? Oh, stupid me. Sorry. Back here with omega. Omega was 2 revolutions. I put 2 pi. That's only 1 revolution. 2 revolutions would be 4 pi. Yeah, that's what I get for trying to be tricky here. All right, so 2 revolutions in a second. Obviously, a revolution is 2 pi. So I missed by a factor of 2. So this should be 0.00282. And then that does agree with the answer. Okay, good. Glad I checked there. All right, so let me come back to the Zoom, because I think we got a number of questions getting started here. So we got some momentum going here. So, all right, so Daniel, let me jump into yours. All right, so you're still in chapter 30, or well, this question is, I know you've already been working in 32, but your question is from number 55. And I'll put a time here of 4:18. Good. Don't worry, Zach, I will get you yours, no matter what the time is here. I won't go too fast, though, with 55, because I don't want to lose anybody here. But chapter 31, number 55 here for Daniel. Okay. So 31 is the chapter I'm in. Let's look at number 55, and maybe I'll start with trying to draw this thing. We've got these rails. I'll just kind of make mine parallel to the writing on my page. Then we got these wheels that connect across. So we got this rolling device. We've got this magnetic field that is pointing down. And so this would kind of be like actually a railroad car, because it's got metal wheels on a metal track. And if you put a resistor here, and I'll call this point A and B and match there, you can hopefully see if I make a loop. Maybe I'll make a loop in the purple here. But here's this loop. Whoops, I shouldn't put a direction. I don't want to put a direction for current here. I just want to make a loop here. But I do want to figure out what the direction of the current is. I think that's one of the questions. Maybe I better read the question. It says in figure 3155, the rolling axis is, and so they say that this is 1.5 meters long. It's pushed along the horizontal rails, so it's being pushed. And so, like if this was a train, it'd be the motor in the train, moving at 3 meters per second. A resistor of 0.4 ohms is connected to the rails from point A to point B, directly opposite of each other. The wheels make good electrical contact with the rails, so the axis, the rails, and the resistor have a closed loop. The only significant resistance is R, a uniform magnetic field, and so B here is, B is 0.08 Tesla, vertically downward. Find A, the induced current. All right, well, the first part of this goes back to chapter 27, where I'll just do Ohm's law. The amount of current is the voltage divided by the resistance. But maybe I'll add it to this chapter by saying, okay, the voltage comes from a changing magnetic flux. So maybe that's I don't know about the hardest, but that's maybe a big step of this problem, is to recognize that I have a loop, I have a changing flux, that's going to induce an EMF. So there is metal pieces. So here is a voltage divided by the resistance is going to get a little bit of current flowing through this axle of the train and the rails of the train and this resistor. Now, I don't think it's going to be much, but it's going to be something that's noticeable, measurable, probably not useful to run anything. So I don't see a train company taking advantage of this and using it for anything, but at least it could be a trigger mechanism that might tell the speed of the train or something. Okay, so this motion EMF is really the big piece. And here's where we can just fall back to our BLV if you like. I'll rederive it if you want. This is then Faraday's law, which says the change in the flux. We only have one loop, so if I do magnitude, I'll get rid of the negative and replace n with 1. And then the flux would be the integral of B dA. And then, of course, the B, and then the integral of dA, and they are in the same direction. That is, the plane of this is horizontal, so the dA is upward or downward, and so the magnetic field is upward or downward. So I have cosine of either 0 or 180, so either way it's 1 or negative 1. And then I just have the B and the A, and then I'm taking the derivative. And of course, the A is the length here times this distance x. And so when you take the derivative, you get the dx, and so we're BLV. So like the last two problems, I'm going to take advantage of the motion EMF. I'm going to say, look, something is moving in a metal rod is moving. In this case, it's the axle of the train. So a metal rod is moving in a magnetic field. All right. So with that in mind, I can answer the first part of this question. What is the current? It would be the magnitude of the field times the length of the axle times the speed divided by the resistance. So they said the field was 0.08, okay. They said the length of the axle was 1.5 meters. They said it was moving at 3 meters per second. And the resistance is 0.4. Now, it's going to give me more current than I thought, but this is a huge field. This would not be like a real train or moving in the Earth's magnetic field. That's a really good size field. So if I grab my calculator, 0.08 times 1.5 times 3 divided by 0.4, and I get almost a full amp. Wow. Which, like I said, it's because the field is a big field. So this would have to be, done with some kind of magnets near the train. Okay, so there's my current, and so that should be A. Find the induced current. So then B, let me call this page 1 and jump over here to B and say, okay, what horizontal force F is required to keep the axis rolling along with this constant speed? Now, you may not have caught this in the other motion EMFs because we didn't talk about it, but let me point out something here. I'll go back to my purple. If we talk about the direction of this current, since the field is going down, as the train rolls this way, there would be less flux down. So to make up for that loss of flux, this is Lenz's law, the secondary field would want to be down. And so I'm going to point my thumb down and then say the current would go from, I guess, B to A, and then across the train axle from top to bottom, back to B. And so we would get a flowing current here we're losing flux. Goes down, we want to make up for it. Okay. Now watch this. This is a current in a magnetic field. So I'm going to go back to chapter 29. We learned that a force would have a force on it based upon the length of it and the magnetic field. And of course, this is chapter 29. It was even a question on the exam. So if anything's hard about this chapter, it is making sure that you don't forget the previous stuff you learned. So I just went through a motion EMF and figured out there was a current. But now I would say if there's a current in a magnetic field, I would do a cross product here. I would put my fingers in the direction of the current, which is down, and close towards the magnetic field. And notice then that there would be a force opposite of the direction the wheels are trying to move. And so that's why they're saying, hey, there would be a slowing down. And we're not talking about the slowing down that any train would have just because of friction. This is a force in additional to the friction. This is an electromagnetic force. And so we induce our own current, but in the process, we have a force on ourselves. That's why this isn't a good idea to generate a current this way. You generate a current, but you don't get it for free. You slow down the train. And so if you're trying to generate a current, fine. So if you have something that's moving and you want to generate a current, so that makes sense. But if you have something you want to keep going, this is not a good idea. This is going to slow down the train. So what I'm going to do is I'm going to calculate how much force is slowing down the train. Because to keep the train going at the same speed, I would have to apply a force, right? This is a net force of 0. I've got to push on that train with the same amount of force in a forward direction that the electromagnetic force is going to be slowing it down because of the force on the current in the magnetic field. So I'll say it again, we can't forget the stuff we learned earlier. And so part of this is the stuff we learned in chapter 29, the force of a current in a magnetic field. But the other part of this is Newton's second law, which we learned last semester. That the net force needs to be 0. And so that's when our physics and engineering problems start to become pretty hard, is we've got all these things going on at the same time. We can't just focus, oh, well, I only need to worry about the current generated for now. I'll worry about the force and the slowing down later. No, those are all going on at the same time. All right, so I'm going to go ahead then and then use this for part B. So the force that is slowing it down would be L cross B. And so if I just calculate the magnitude of that force, it's the current times the length times the field times the sine of the angle between them. And that's 90 degrees. I'll come back to the picture. The current's going down and the field's going in. So this is going to come down to a current of 0.9, a length of 1.5 meters, a magnetic field of 0.08. I think that's what it was, yeah. And then, of course, sine of 90 degrees is 1. So grabbing my calculator, 0.9 times 1.5 times 0.08 times 1 is a force of 0.108 newtons. So I wouldn't call it a large amount of force, slowing it down. But nonetheless, it is a force slowing it down. So I would need to apply that much force in the forward direction, and that would be the answer to B. What horizontal force F is required to keep this axle rolling at a constant speed? Now, C is really Lenz's law. Which end of the resistor, the A or the B, is at a higher electrical potential? Well, coming back to our discussion in the purple here about what direction the current is flowing, we came with a clockwise motion. So that means since the current flows from high to low potential, it goes down in potential here, so we'd have to go from B to A. So it would flow which, let's see, what does it say? Which is at a higher, so B is higher
You
than A.
remind me how you came up with how we got it going clockwise, the current?
Yeah, and since my picture is kind of messy, I'm going to start with a new one. And so here's the rails. Here's the resistor. For simplicity of drawing, I'm just going to put a metal bar looking thing across the rails and remind myself and you that it's moving towards the resistor. And then also remind myself that the field is going down. So if I did kind of a cross-sectional view, I would draw a magnetic field with green circles with an X. And then this is Lenz's law. Lenz's law is we oppose the change. So in my picture, you might say that I've got 4 magnetic field lines going through this loop. And as it moves over to say here, we're going to have less. So we're decreasing it. Remember, we oppose the change. So to get 2 more back is required. We want to get back to where we were. So we want flux to go in. So I'm going to take my right-hand rule. Remember, my thumb is going to be the direction of the flux, so I'm going to point my thumb down. I want my current in a direction. If I look at my fingers now, my fingers are curling around in a clockwise direction.
Oh, okay, I see.
My thumb points down, yeah. So the current would be going in a clockwise direction.
So that's right-hand rule number 2.
Yeah,
right?
right-hand rule number 2. And in this case, I'm using because right-hand rule number 2 can be used either way, but I'm using my thumb for the field and my fingers for the current.
Okay, that makes sense.
And so the first important piece was to find out which way I want to put my thumb. And that's opposing the change. And so I knew my thumb would go down because as I moved across, I lost 2. So to gain those 2, I want the current to be some direction, either clockwise or counterclockwise, so it goes down. So thumb down. And then look at my fingers. Yeah.
Okay.
Now, I think we have to do that right-hand rule again for D, because D is saying after the axis rolls past the resistor, does the current in R reverse direction? Let's go through the right-hand rule again to answer this. Let me put the resistor over on the right-hand side of my picture now. And so my metal rod is now moved past it. Now, so I can kind of see the field, let me again put green circles with an X. We'll just do 4 of them. And in my picture, 2 of them are going in. And so as this thing moves, I would have another 2. So that would be an increase going downward. Now remember, Lenz's law says you oppose the change. So if you have 2 going in and then you move so that there's 4, so you move to here, the current would be set up either clockwise or counterclockwise with the magnetic field from the current coming out, because we want to get back where we started. We oppose the change. So in other words, as we move the metal bar, we get 2 more going in from the external field. The current then sets up so that the field comes out, the secondary field. So you still have a total of 2. You keep it the same. So I know I want to point my thumb out. So I'm going to go to right-hand rule number 2. I'm going to point my thumb outward. I'm going to look at my fingers, they curl around in a counterclockwise direction. Now, if I'm not careful, I will say, well, that's opposite. It was going clockwise, now it's going counterclockwise. Well, okay, but that is still, whoops, not there, at this resistor, that is still from the bottom of the resistor up. That is still from point B to point A. And so I would say in the resistor, it hasn't changed direction. It went from bottom to top before we got to the resistor. Then after it passed the resistor, it's still going from bottom to top.
So is that because when you put your thumb up,
Yeah.
Coming out of the page, your fingers curl towards B?
Well, my fingers curl in this direction.
Yeah.
Counterclockwise, yeah. So it would go counterclockwise, which comes towards B and then up to A.
Okay. So the direction of the current changes, but the actual flow through the resistor stays the same.
Yeah, I would say it a little different. I would say before we got there, it flowed, and the whole loop was clockwise. Now afterwards, it's counterclockwise. However, their question was very specific. It says the direction in the resistor. So I guess what I'm saying here, you could imagine a loop here going, so here's my circle. And if I were to go, well, here, I'll do a smaller circle so it fits better on the screen. But if I were to go clockwise on this edge, it's going from bottom to top. Now, if I take that same circle and flip it over, ouch, can't quite get there. Now it's going counterclockwise, but on that same edge over here, because it's the other edge, it's now going still bottom to top.
Okay. Cool. The other ones kind of made sense, but the last question just really did not make sense to me. So
yeah, maybe I should check my numbers. Let's see, A looks good, and B looks good, C looks good, and then yeah, D says no, the magnetic flux will increase through the loop of the left would be to A here, and they got a little right-hand rule going on. Yeah. But I think they could be more specific, because it does change in the sense it goes from clockwise to counterclockwise, and some would call that a change in direction, and I would call it a change in direction in focus of the whole loop.
Mm-hmm.
But in terms of the direction in that resistor, no, it's still from bottom to top. Yeah.
Cool. Thank you.
Sure. All right. No, so, hey, I know, Zach, I said I would get to yours, and I hope you still have time. We're a little bit over our time frame, but it's probably well worth going through this one for you.
Yeah, I actually I very much have time, and I appreciate you sticking around to do that.
Good. Because you said, let's look at, what was it?
25 on chapter 31.
Number 25. I'm going to write this down. We are at time.
Have a good weekend.
4:40. All right, you too.
Have a good weekend, Daniel.
So let me do chapter 31, number 25. And let me find number 25. Oh, I'm looking at the solution. That's not helpful. But yes, this is this homopolar generator. This one's kind of.
I was looking at the section in the book and just like, there's a lot here for this.
Yeah. This
is kind of a dense spot.
This is a little hard to see. But since you were sitting here while I did the helicopter one,
Yeah, yeah, it was.
Okay. I'm going to use that as a springboard. What number was that? Was it 27?
Helicopter one, I believe. Yeah, it was 27. Yes.
Okay.
Yes, yes.
Let me just.
I will say, unfortunately, I didn't write down everything for that one because I was working on an earlier problem in the homework set leading up to 25. It's just like I identified that one early on. I was like, I know that one's going to be a mess for me. So
Okay.
I figured throw that up there.
Okay.
And,
well, then maybe I'll just start over. But this is kind of like a helicopter. See how it's a spinning disc and the helicopter blade was a spinning. So there's some comparison there.
Okay.
But let me just derive
Which
this.
I could absolutely appreciate, a comparison, even after having worked through it, and maybe just talk over points where it's like, hey, this correlates. I'd be into that too, because any of that would help me with understanding this stuff. For sure.
Yeah. Okay. So let me do this because it's actually a whole disc that's spinning. But what you're going to do is make electrical contact between the rim of the disc and the center. And so you have this like metal piece that slides. We call those brushies.
Okay.
And so our circuit looks kind of like this. We would put whatever we want to operate, like let's just say a light bulb that has some resistance. And if we just take this spinning disc that has a magnetic field perpendicular to it, it is essentially at that moment in time a metal rod sticking out. Of course, then it turns and it's a new metal rod, and then it turns and it's a new metal rod. But for that instant in time, that's why I said it's going to look just like a single blade of this helicopter. And I'll cross out the result from 27. Let me get that result again. And the way I got that result was to say this. And so I'll draw a long blade here. I'll just call it a helicopter blade, but it's really this piece of metal that is connected from the center of the rotating disc to the rim. And so here's the center, and here's the rim. I'll put rim, center. But why don't I take a small little piece of it, and I will say that it has a small length of DL. I pick that because the motion EMF was that we get a voltage that is created by these three factors: the strength of the magnetic field, the length of the metal bar, and the velocity that it's moving. So if I take the equation from the motion EMF and apply it to a small piece, I guess my L would become DL. My voltage would be a small piece with just this length, so I'll call it D script E times V. If I realize this is rotating around with a speed omega, I'll need to go back to physics 121 for this, but the velocity would be the position, how far away is it from the center, r, times the angular speed. In fact, maybe one more step might be appropriate here. Since we're talking about a length that would be going radially outward from this, whatever you want to call it, helicopter blade or a section of metal wire in the disc, let me call it a DR. Because then to do that for a second little piece and a third little piece and a fourth little piece and a fifth, the total voltage from the center out to the rim would be then adding up all the pieces. It would be integrating. And so I would start at R equals 0, maybe this first one here, and keep going until I got to, and I'll go capital R for the radius of this disk. So the B and the omega would be the same, and I would now just, or be a constant, excuse me, and I'd pull them in front, and then I'd have an integral of R dr, which makes R squared over 2, and I would evaluate it from 0 to capital R. So let me actually put this as, so there's the B, there's the omega, there's the R squared, there's the 2. And so if you get a chance to go back and watch the recordings here and you see that helicopter one, that's what I essentially did for the helicopter. I just called it the length of the helicopter blade. I didn't call it the radius of the disc, but we're talking about the same Oh, I wrote it wrong. My bad. I'm glad we went through it. I wrote it down wrong. Oh, let me just check that helicopter. Did I do it? I hope I didn't do it wrong for, I think that one was for Hunter.
It was. I didn't think you
Oh,
did.
oh, good.
I did get a glance. Yeah, I did
Yeah,
glance over
here it is where I worked it out. So it was an L squared.
Yeah.
I just wrote it down wrong.
Okay.
Oh, yeah. Oh, and I think we even checked the answer. So I should have known. All right. So that's, I think what the author wants you to do is to start here. You know, not necessarily derive it, but he does this one on, I can't remember the page, but it's section 2 in 31. He does the helicopter one. I didn't say that when I was helping Hunter, but I was going to say, look, just, you know, they did the helicopter one as an example.
Right.
So just plug and chug and you're done. But I wanted to go through it. So anyway, I wanted to go through it again a second time with you. All right. So now it just becomes a plug and chug. Let me go to 25 here. It says where ultimately, this is a long one. It says find the EMF generated between the brushes. So there's the equation. It's B squared omega R squared over 2. So for this one, they've put it in a really strong field, 0.9 Teslas. They're spinning it at a really high rate. The only thing I would caution you about is it says revolutions. So I'm going to change that to 2 pi radians.
2 pi radians.
They also have per minute. So I'm going to put 60 seconds.
Mm-hmm.
Then we've got the radius squared, which is 0.4. So I'll square that. And then the factor of 2. So grabbing my calculator, 0.9 times 3200 times 2 times pi times 0.4 squared is the numerator. Divide that by 2 and divide that by the 60 seconds. Looks like about 24.1 volts would be the answer.
Yeah.
And I suppose I should check 24.1. Yay, good. And I got the same that they did. Nice.
All right.
All right.
I guess, I mean, yeah. I mean, starting from the formula doesn't seem like a massive leap, I guess. It's just, I was having a hard time connecting or deriving it on my own for that one, I guess.
Yeah, well, and I would say yes. Yes, this is one of those problems where once you realize the formula, it's just plug and chug, and that's the easy stuff.
But
The
you gotta
hard
know when
part
to use it.
is, yeah, when to use it. And you could either derive it yourself, as I just did, but you could just as easily, and I think this is what the author really wanted you to use the formula that he derived in section 2. However, the hard part was to recognize that that was a valid equation. And so both the helicopter one and this one, and I think the helicopter is a little bit easier to recognize because he simply says in that example, take a rod of length L and rotate it. And that looks very much like the blade of a helicopter. Whereas this one, you've got to say, okay, this too is functioning kind of like that helicopter with a continuous set of new blades coming in. But either way, once you recognize that, I don't think he wanted you to derive it, but I think we learn more by deriving it. So I did that.
Yeah, which I was hoping for and appreciated. So, yeah. All right. Well,
All right.
Thank you very much. I'm glad that I got to ask that question. And yeah,